Okay, it's time to start class. It's Math 1151. Today we're going to talk about Newton's method. And the first thing you should know about Newton's method is that it's a recursive formula. It's recursive. Now this is something that you might not be used to. I think when I kind of explain it to you, you're going to say, oh yeah, I get that, that's okay. But you might not be completely used to it. So here's an example. I'm going to write a pattern on the board, and then you can tell me how I'm getting the next one. So the first number in my pattern is 1. The second number in my pattern is also 1. The next number in my pattern is 2. And the next one is 3. This guy said it, right? And what's the next one? The next one's 5. And what's the next one? 8. And the next one is 13. Now, there's lots of patterns that I can be doing. But by asking you the question, you're going to guess that I'm going to be thinking of one that you can figure out pretty quickly, not something that's too complicated, right? It's a little game we play. And so how do I get to the next number? What do? I add, that's what this guy's telling me. He says, I add the previous two numbers to get to the next one. So 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. 3 plus 5 is 8. 8 plus 5 is 13. The next number is 8 plus 13, which is 21. This is the Fibonacci sequence. And it appears, how to say that, in nature sometimes. And the reasons are a little bit complex. But they're pretty cool. All right, so what's this have to do with Newton's method? Well, you can write a recursive formula. And here's the recursive formula for the Fibonacci sequence. What I could do is I could write A naught. This is A with a little 0. I could say this is 1. And so this is like A naught right there. These are equal. And I could say A1 is also equal to 1. And so here's A1, and it's equal to 1. And now I want to explain the rest of the Fibonacci sequence without writing it all down, because there's too much. And so I write this. I could write dots. I'll write some dots here. A sub n plus 1. This probably isn't visible on the camera. I need to watch some of these videos more closely. A sub n plus 1. So there's a little n plus 1 here. So this is the 0th term. This is the first term. Skip a few. The n plus first term. And how do we make the Fibonacci sequence? We add the previous two, right? And so this is going to be, the previous one is the nth term. And the one before that is the a n minus first term. She says, very good question. If you say first term, Bart, do you mean the 0th term of the first term, right? In this context, I'll always say the 0th term when I mean the initial term. All right? So this is the 0th term. This is the first term. So let's just do one more example of this just to make sure that it's it kind of makes sense. All right? And so look at this. If I wanted to know 1, 2, 3, 4, 5, 6, 7, 8, I don't know. Let's just try it. If I wanted to know A10, so this is A naught, this is A1, this is A2, this is, well, that's interesting. A3, A4, right? Are we okay? So if I wanted to know A10 is equal to A9 plus A8, right? And so I could go through A2, A3, A4, A5, A6, oh geez, A7. Okay, and so I need A8 and A9, right? And so I could add, what's 13 plus 21? It's 34. Thank goodness somebody can add. And then what's the next one? 55. This is A9. Isn't it 56? No, it's 55. Okay? And so now this is equal to 55 plus 34, right? And so that's 89. Is that right? I heard somebody whisper yes to me. So usually when people whisper things to me, it's either right or wrong. All right, and so there's A10. So this is a recursive formula. Now Newton's method is also a recursive formula. And I'm just, I teeter-totter between telling you like the formula and then the idea, or the idea and then the formula. So I'm just going to tell you the formula first, then we'll talk about the idea. If you have strong feelings on this, you can send me an email and tell me your feelings, I guess. Okay, so this is Newton's. I'm going to write it here because I want more space. Newton's method. I remember thinking when I first learned this that this was pretty cool. You may not think it's pretty cool, but hey, to each his own, right? So I remember I thought this was pretty cool, and I wrote a little computer program that would run it for me on my TI-80, whatever it was. You know, so you could do the same thing if you wanted to. So we have a differentiable function. Of course, I spelled function with no vowels. F of x. We have some differentiable function f of x. Okay, so, and we want to solve, we have this, period. We want, you know what? We're going to write this in pink. We want to solve f of x equals 0. Newton's method is about solving equations. Produce a sequence of points. We're going to produce a sequence of points, and these are going to be closer and closer and closer solutions, hopefully. Sometimes they're not. And they're going to be called A0, A1, A2, and so on. And here's the form. It's via a recursive formula, just like the Fibonacci sequence. And here's the formula we use. AN plus 1 equals AN minus F of AN over F prime of AN. Now, there's something I haven't told you yet. And if you're paying attention, you might know what it is. Wait, if you're paying, you might not know what it is, too, if you're paying attention. What do I need to tell you to give you a recursive formula? There's something I'm missing here. I haven't told you something yet. I haven't told you f of x. I also haven't told you, remember here I gave you the starting point, right? So that you can work backwards. Here I haven't told you what the first, when you tell somebody a recursive formula, you got to tell them a starting point, okay? A0 is a guess. You just guess A0, and then you build your sequence. And you hope that it works. Now, the good news is you can always tell if it's working. Because what do you want? You want this, right? Oh. And so And so what, end result, how about I'm going to put one more thing up here. End result. Can I write down here? Anybody? Yeah? End result. For large, in quotes, n, we hope f of a sub n is about 0. So these are getting closer and closer to our hopeful solution. This is super useful. If you have to solve it, solving equations is super hard. I mean, super hard. Like, you guys could write down equations and say, Bart, try to solve this. And I'd say, I cannot. And I can't. You say, well, what about if you use a computer? I'd be like, well, maybe I can now, but I bet you could still write down equations I couldn't solve. You know, very hard. Symbolically. This is a numerical way of finding a solution, and it's actually pretty easy. We can understand it, okay? Why? Let's see if I can explain what's going on and why should this little trick work. Why should we, how did Newton come up with this method? You know, let's see, well, Newton was, you know, super clever, super clever, but also his method makes sense. And that's what's so cool about it. It's like, if you start to think about it, it's almost like the most obvious thing you might try to do. Okay, so this is f of x. That's the point we want to know. All right? We want to know that point. But you know what? We might have trouble solving this. We just don't know how. And so you make a guess. You make a guess that you think might be close. Okay, this is ridiculous. Okay. You make a guess, and you put it here, maybe. Here's your guess. A, not. There's my guess. It's not really close to the root, but it looks good enough for me for now. And then what Newton's method does, what this is it's going to find the next point, and here's how it does it. And we'll work through this. It's not too hard. It takes a naught. It evaluates it at the function. And then you compute the linear approximation of the function right here. And you get a tangent line. And can we solve linear equations all right? We can always solve linear equations. And then this is our A1 right here. There's our A1. And so, how do we get our next better guess? We plug it into the function. Find the linear approximation. Here, I'll make it in a different color. Why not? Right there. And then solve that linear equation. And look, already after 3 steps, we're getting pretty close to a solution. You see what I'm saying? This is A2. It's so close I can't even draw another one without just making a mess. Does that kind of make sense, the idea? In practice, this seems to work pretty well. I think I've talked about it before. You might be tired of hearing about it, but I did some work for a steel mill with a robotic arm and laser and stuff, and we had to solve an equation that was really bad. There was no way to do it except with Newton's method. And typically, we could have it go through 6. We could just find 6 points, and it would be beyond the accuracy of the machine that was being used. And so we said, well, that's good enough. You know, you're right. We're beyond the accuracy of anything we have, and we only had to go through 6 times. I don't think 6 times, for a computer, 6 times is not a lot. 100 times is not a lot. You know, like 1,000 times. I don't know. But anyways, it's pretty cool. Okay, why, what, okay, now what we should explain is, I think this should make sense, right, why this works. What's the connection between, what I'm going to try to explain next is what's the connection between this thing and this formula right here. Like where do those, like how are they connected? I'm not sure if that's totally clear. I don't think it is. So let's see if we can figure this out. It shouldn't be too hard. We can do it. And it's going to reinforce some of the ideas that we've already talked about in this class, which is why we're doing it. One of the reasons why. All right, so what do we do? So AN, so I'm explaining this formula right here is what I'm doing. So A sub n is our current guess. That's our current guess. It's like A sub 1 here, right? This is like A sub n. What do we do first? We plug it into the function, right? Plug it into the function, and then we find the line that goes through the function. We find the linear approximation at this point. Does that make sense at all? What's the slope of this line? What do we use to find the slope? We use the derivative to find the slope, right? So f prime of, okay, so this is our current guess. F of an is a point on the curve. F prime of an is the slope of the tangent line. At an comma f of an. So I'm just saying that this is the slope of this tangent line here. All right, and what's the formula for a line that goes through a point with a certain slope? Yeah, we got the point slope formula, right? And I just write the darn thing out. Y equals the slope, f prime of an times x minus x naught, right? X minus x naught. So that's going to be x minus an plus f of an. There we go. There's our point slope formula. That is a linear formula. I don't care that it has only letters in it. I don't care that it has subscripts and primes and whatever. It just is a line. I can solve any linear equation you give me. I hope I don't have to eat those words, okay? But I'm pretty sure I can solve any linear equation you give me. So what's it mean to solve? Well, we want to know when this line goes through the x-axis. So we're going to say 0 is equal to f prime an times x minus an plus f of an. Solve for x. All right, I can do that. So this is going to be minus f of an is equal to f prime of an times x minus an f prime of a sub n. There we go, looking good. Looking good, Bart. And now, let's see, what am I going to do now? Oh, I'm going to add to both sides. I'm going to add this. God, I want to call it a bozo. I want to add this thing to both sides, and I'm going to have an f prime of an minus f of an equals f prime of an times x. I hope this is on the video. If it's not, everything's going to be very confusing forever. Okay, so now we divide both sides by this thing here. And when I divide both sides, look, this is going to cancel, right? This is going to cancel, assuming the derivative is non-zero. Then we can divide. So, and we're going to get an minus f of an divided by f prime of an is equal to x. And this is our next guess, and I didn't lie to you yet. Did that make any sense to anyone? It made sense to me, so that's pretty good. But it would be good if it made sense to somebody else, too. And if not, you can ask a question. Or you can just cry uncle and say, go on to the next thing. Oh, thank you. He's asking, what's going on here, Bart? This is too messy to be comprehended. This should be an minus that. See? I apologize. My bad. What's up? Yeah, the x is going to be your next guess. And you can see how a computer could do this, because it just loops through and does this. And you might say, well, how often is it that you have a function that's differentiable, that you can differentiate, where you can evaluate it? Well, it seems to be pretty often. This is a good method, and it can get you as close a solution as you want. That's the idea anyways. So if you ask yourself, how do we ever know what the square root of 2 is to 20 decimal places? What's up? If this is asked on the test, he says, what if this is asked on a test? How many times should we do it? We better tell you, okay? We had better tell you. Or likely, this is, so we had better tell you, or we had better tell you to so many decimal places. And all you do is you wait till your decimal places stop changing. All right? Yeah. She says, why does x equal an plus 1? It's because, remember what's going on here. First we guess. We go up here, find the linear approximation, see where the line intersects. This is our solution there, our x right there. Okay? And then that becomes our next guess. So x equals a1 now. Put it in here. Now x is, did I sort of answer your question? Okay, good. This is really cool because you can do it in higher dimensions too. If you have 8 variables, you can do the same thing. The picture's not as nice. I can't draw it, but it works. Okay, let's see a real example of this. Let's see. Whew, God. Let's see a real example of this. Here we go. So before, we estimated the cube root of 50 using a linear approximation. Do you guys sort of remember doing that? I only sort of remember doing that. Okay, so we want to use Newton's method to approximate x cubed equals 50. Now look, this is, when I say x cubed equals 50, oh, this is perfect. X cubed equals 50. This is the same thing as approximating the cube root of 50, right? Being able to fluently switch between the cube root of 50 and x cubed equals 50, that's a trick of calculus. That's a trick that we learn in this class. It's often not talked about, but it's something that we kind of expect you to do. All right. So we're going to set f of x equal to x cubed minus 50. That's the first step. F of x equals x cubed minus 50. And now what we're going to do is we're going to make a guess. We're going to make a guess. Do you guys, oh, what's f? We should compute f prime too. F prime of x is equal to Awesome. 3x squared. Outstanding. All right. X cubed. Tell me what's a good guess? You should try to get as close as you can. As a rule of thumb, you should try to get as close as you can. 3.5. Can you tell me something that's easier for me to cube, actually? 4. Okay, so 4 will be our first guess. So we're going to guess 4. Why are we guessing 4? 4 cubed is equal to 64. And 64 is close to 50, sort of. Right? All right. So the best thing to do here is you make a table. You make a table. We'll have n here. A naught. Put 0. Sorry, 0. An. F of an. Might have gone crazy with this table. And then this is our next guess. An minus f of an all over f prime of an. So 0 is our first guess. And we already, I basically demanded that we pick 4 as our first guess. So 4. This is A0. What's f of A0? What's 64 minus 50? 14. All right, and so now what we're going to write here is 4 minus 14 over 3 times 16. What's 3 times 16? 48. Which is about 3.708. It's about 3.708. And so n equals 1. What's A1? 3.708. By the way, what's 3.708 cubed? Yeah, he has a calculator. He could 3.708 cubed. Okay, so at this point, we're at 50 point, this cubed is 50.98, right? What should it be? 50. We're already close, right? We're already pretty darn close. Let's go ahead. Okay, so now, here we go. This is 50. Wait, what is f of an? So f of an is about 0.98. We're only 0.98 off of the square of the cube root of 50. And so what's this thing now? Well, it's going to be 3.708 minus f. So that's going to be 50.98 divided by f prime. Oh, I don't know what f prime is. F prime is going to be this squared times 3. Shouldn't this be 0.98? You are 100% right. I was trying to be smarter than me. Doesn't work. Yeah, what's up? Two. She's wait, are you asking me if we always approximate this to 2 decimal places? Are you asking if I always find this to 2 decimal places? Yeah. She's asking if you always, no, you do what the problem says. Problem says to 2 decimal places. Yeah. I didn't write that. Okay. F prime. I mean, I can't do this in my head. I'll put a question mark here, and this is about 3.684. And so now this becomes 2, and then put 3.684 here. And if we compute f of 3.684, so what do? We take 3.684 and we cube it, and then we subtract 50, right? What are we going to get? Negative 0.002, right? Are we pretty darn close to being right on the money now? Yeah. And so, and the next one, by the way, is about 3.684. The answer stops changing very much. We've converged to the correct answer. What questions do you guys have about this? Yeah, what's up? Yeah. Right. She said because it went negative, it means you went under the point. That's one way to look at it. Remember, x cubed minus 50 looks like this. X cubed minus 50 looks like this. And so if you're a negative, what you did was you actually picked a point slightly to the left. Right. Yeah. The final answer is 3.68. Because, okay, we're looking for a root of this. And as we're plugging numbers in, so x is approximately 3.68. How do we find this number that I put a question mark up for? It's not hard to find at all. You take this number here, and you plug it into f prime of x. 41.24. All right? So this is Newton's method. Now, there's a slight problem with Newton's method, just a little one, and that is that sometimes it doesn't give you the right answer. All right, so let's go ahead and see what happens here. And it's not such a big, you might think, oh, that's terrible, it doesn't give me the right answer. Well, you're constantly checking to see if it's the right answer because you're constantly plugging it back into the function, right? You'll know. You know, basically you tell a computer, hey, do this 100 times. Have you gotten the answer yet? No. Make a new guess. Newton's method depends on the guess you make. So let me show you an example of that. If you make a particularly bad guess, then it doesn't work. So suppose, this is going to be kind of a stupid example, because I'm just trying to show you something. I'm trying to give you the easiest example that shows you a bad guess, right? So you're going to know what the right guess is immediately, and you're going to be like, Bart, why did you pick that stupid guess? And like, well, because this is a bad guess. Suppose you want to solve square root of x is equal to 0. What's x equal? 0. Okay, you have to suspend your disbelief for a second and say, pretend I didn't know this. All right? And you say, what could it be? I don't know. Maybe it's 1. X equals 1 sounds like not too bad of a guess. This is our first guess. A naught equals 1. By the way, f of x is equal to x to the 1/2, and f prime of x is equal to, let's see, 1/2 x to the -1/2, right? So our little formula here, an plus 1 is equal to an minus x to the 1/2 divided by 1/2 x to the minus 1/2, isn't it? What's x to the 1/2 divided by x to the minus 1/2? It's just x, because this flips over, so this is going to equal an minus 2. Sorry, there's no x here. an minus 2an. Oh, what's an minus 2an? Minus an. So what this is telling you, okay, so what's our first guess? What's our first terrible guess? 1. So we're using Newton's method. Oh, and I can probably draw, if I'm smart, which I might be, I can draw a picture showing you what's going on. Maybe. Okay, so A0 equals 1. A1 is equal to minus 1, right? A2 is equal to 1. A3 is equal to minus 1, and so on, right? It just bounces around between 1 and minus 1. Does it ever get to 0? No. Why does this happen? Well, I don't know. I haven't tried to draw a picture yet. Let's see if I can just draw a picture. I bet I can. We should be able to just draw a picture of this. This is a simple enough idea. Shouldn't be a total disaster. I mean, another sort of foundational goal of calculus is to give you guys some feeling for what functions look like, so you can do exactly the sort of analysis that I'm going to attempt right now. There, that's like the square root of x, right? Don't mess this up, Bart. All right, so there's 1. There's our first guess, right? How's Newton's method? How does Newton's method work? We go up here, right? And then we draw the slope of the tangent line. Up, there's minus 1. There's our next guess, right? Yeah, we have a big problem because it doesn't exist at that point, right? All right. So that's one thing that's really causing us problems. Good. Now let's do one more example where it does exist, and we're still going to see problems. Okay? And we're going to this time it's going to be a cubic. Yeah, Newton's method needed the function to x cubed. We're going to solve x cubed equals 0. You really don't need to write this down because, again, this is just kind of showing how things can go wrong. And then I'll do some more examples that maybe you should write down. But this one, we should just kind of pay attention, make sure we understand. Okay, again, we're going to make the bad guess of A0 equals 1. We're trying to solve this. 0 solves this, obviously. We'll make the bad guess of A0 equals 1. And let's see, what is f prime of x is equal to 3x squared. No. Yikes. I'm sorry. I want to solve the cube root of x equals 0. So f prime of x is equal to what? 1/3 x to the minus 2/3. Right? So now, an plus 1 is equal to an minus f of an. So that's going to be an to the 1/3, right? Over 1/3 an to the minus 2/3. This is equal to an minus 3 to the an. And what's an minus 3 to the 3 times an? Yep. Yep. Equals minus 2 an. Okay, so now, again, we're making the stupid guess of a naught is equal to 1. What's a1 equal to? Negative 2. a2 is equal to negative. You plug this into here. Negative 4. a3 is equal to negative 8. This is not getting closer and closer to 0, right? Positive 4, my bad. All right, so now let's see if I can draw this one. The cube root. Okay, so the cube root looks like this. And then cube root of a negative number is obviously negative. Okay, there we go. Looks kind of like that, right? So I guess 1. There's 1. I guess 1. Here's my negative 2, right? Now I guess negative 2 goes down to here. And then here's my 4. You see what's happening here? And I go up here. Whoops, draw the tangent line, Bart. And then this is supposed to be my negative 8. This is how we're getting farther and farther from the root. Now, if you would pick better guesses, and you can typically just pick a random number kind of close. All right. So this is the basic idea of Newton's method. Let's work one more problem, and then I think we're done for today. All right. All right, here we go. Last problem for today. F of x equals x cubed minus 4x squared minus 5x minus 7. We're just going to start approximating this and see how it goes. In the 1500s, this is a cubic equation, right? This cubic equation would be kind of difficult for us to solve. We can solve it. There is a cubic formula, but do any of you know the cubic formula? No, it's pretty bad, all right? And in the 15th century, before calculus was discovered in the 17th century, people used to challenge each other to solve problems like this and have sort of a mathematical duel. And then the person who solved the most questions was the best mathematician. All right, so we're going to get an approximate solution using Newton's method. All right, so here we go. This is a sort of reasoning you need to use. So where should we guess? Can anybody make a guess as to where to guess? What'd you say? He said 5. 5 wouldn't be such a bad guess, really. One thing you should do is you should use the intermediate value theorem to help you out. Can you tell me any place where you are, where the function is negative? Like, plug in a number and find a negative number out? Yeah, so if x is equal to 0, f of x is equal to minus 7. Right? What, can you give me a number where you plug in a number and get a positive number out? This guy's shaking his head no. 9? 9 might work with 10. What if I pick 10? 10 cubed is 1,000. Minus 400 is still positive, right? Minus 50, still positive. Minus 7, I haven't been keeping track of what it is, but I know that it's positive. So f of, how about I do this? F of 0 equals 7. F of 10 is greater than 0. Therefore, so by the intermediate value theorem, there must be a root between 0 and 10. There must be a root. And 5, why not? Let's pick 5 as our guess. Okay? So we're going to say A naught is equal to 5. Looks good. He said 5. Well, it's between 0 and 10. Yeah. Any of those numbers are, we don't know anything. All we know is that it's negative at 0 and positive at 10. Any number between 0 and 10 is just as good as the other. All right? Let's hope the function doesn't do anything screwy. So we can make a chart, and why don't we do that? So n an f of an. You know you're getting close when this thing becomes close to 0. That's the idea. And an minus f of an all over f prime of an. Looks good. Okay, so I should compute f prime. Boy, I really should do that. Okay, so here it is. F prime of x is equal to 3x squared minus 8. X minus 5. 3x squared minus 8x minus 5. Does anybody agree with that? Okay, let's just see if we can get close to this root. So n is equal to 0. An is equal to 5. What is, can somebody compute f of an for me? -7. Outstanding. F of 5 is also -7? That's what you got? Okay. Very good. Whatever. Okay, so now, what is this number here? It'd be good if more than one person did this, then we can check ourselves. What'd you get? For this number too? No. He got -7. I believe it. For this number, anybody? $30? Awesome. 30? What? 30 is f prime. 5.2? Okay, 5.23. And so now you should plug 5.23 into there and see if it's close to 0. And if it is, then we're on our way to finding the root. This is our next guess. 5.23. The class is over.